Welcome to solverfy.
In this question, it describes an experiment of magnesium boride reacting with acid and producing a mixture of boron hydrides, 3 of which are liquids and 1 is a gas. When 1 gram sample of each of the liquids is transferred to an evacuated 750 milliliter container, the liquid ends up creating corresponding pressures at 70 degrees Celsius. We can use these pressures in order to answer the question to determine the molar mass of each liquid. First, let's define molar mass. Molar mass is equal to the grams of the substance, in this case it's 0.1, divided by the moles of the substance. The moles can be calculated for each of the gases using the ideal gas law. Rearrangement of the ideal gas law gives us N is equal to PV over RT. We know P for each of the gases, so using P for each of the gases, the volume, 750 milliliters or 0.750 liters, R, 0.08206, and T, 70 plus 273 to get our temperature in Kelvin. For the first liquid turned into a gas, we get a mole value of 0.001585. So to calculate the moles for the second one, the only difference will be the pressure. The equation is going to be exactly the same. We're just going to change the pressure. So we use the pressure provided for the second boron hydride. And we get 0.001876 moles. And then for the third liquid turned into a gas, creating a pressure of 0.05767 atmospheres, we get a mole value of 0.001536 moles. So to calculate the molar mass, now all we need to do is take the moles we calculated and divide it into the mass, each of them being 0.1 grams. And we get a molar mass for the first boron hydride of 63.09 grams per mole. For the second one, we take 0.001876 divided into 0.1 and we get 53.30 grams per mole. And for the third one, we take 0.001536 and divide it into 0.1 and we get 65.10 grams per mole. This is then the answer to just part A, determining the molar masses of the 3 liquids. For part B, the boron was determined to be 85.63 by mass, 81.10 by mass, and 82.98% by mass for liquids 1, 2, and 3 respectively. So knowing the molar mass and these mass percents, you should be able to now determine the molecular formula for each of the compounds, each of the liquids. To do this, let's assume that we have 100 grams of the sample. If we have 100 grams of the sample, sample 1, and 85.63% by mass is boron, then we have 85.63 grams of boron. We can convert those grams of boron into moles of boron. We'll then do the same thing with the second element, which is hydrogen. This is the only other element that is present in the boron hydride. So the remaining percent out of 100 is hydrogen. The remaining percent out of 85.63 is 14.37. So if we have 100 grams of the sample and it's 14.37% hydrogen, then we have 14.37 grams hydrogen, which we can convert into moles of hydrogen by dividing by the molar mass hydrogen. And these would then be the relative moles. For every 7.29 moles of boron, we have 14.26 moles of hydrogen. But it would be nice to express this ratio in whole numbers instead of decimal numbers. So we'll divide by the smallest one, and we get 1 mole boron for every 1.8 moles of hydrogen. If we multiply both of those by 5, we should now get whole numbers. For every 5 moles of boron, there are 9 moles of hydrogen. So the empirical formula would be B5H9, and this would be its molecular formula if B5H9 has a molar mass of 63.09 that we determined earlier. And it does. So this empirical formula is also the molecular formula. Now moving on to liquid 2, which is 81.10% boron. So it would have 81.10 grams of boron if we have 100 grams of the sample. Divide that by the molar mass and we get 7.502 moles. Then the remaining out of 100 with 81.10% being boron is 18.90% hydrogen. So in a 100 gram sample we have 18.90 grams of hydrogen, which we can convert to moles of hydrogen by dividing by the molar mass hydrogen, and we get 18.75. So this sample, we have 18.75 moles of hydrogen for every 7.502 moles of boron. We'll divide by the smallest in an attempt to get whole numbers, and we get 1 and 2.5. So if we multiply both of them by 2, then we have 2 moles of boron for every 5 moles of hydrogen, giving us an empirical formula of B2H5, which has an empirical formula molar mass of 26.6. This is not the molar mass that we determined for compound 2 on the previous slide. It was 53.30. So if we divide our 26.662 into the 53.30, we get 2, which means 2 will be our subscript multiplier that will multiply by the 2 subscripts up here to convert the empirical formula, B2H5, into the molecular formula, B4H10. And for the last one, we have 82.98% boron. So a 100 gram sample gives us 82.98 grams boron, which we can convert into moles boron by dividing by the molar mass boron. And then what's left out of 100 is 17.02. We'll convert those 17.02 grams hydrogen into moles of hydrogen by dividing by the molar mass of hydrogen. And we get 16.88. So we have 7.676 moles boron for every 16.88 moles hydrogen. Divide by the smallest in an attempt to get whole numbers, and we get 1 and 2.2. If we multiply both of those by 5, we get 5 and 11. So the empirical formula would be B5H11, which has a molar mass of 65.14 grams per mole, which is the molar mass of the compound we determined on the previous slide. So the empirical formula, B5H11, is also the molecular formula. Now for part C. Part C is in reference to the 4th sample that was a gas. It describes its diffusion rate with respect to sulfur dioxide. Knowing its diffusion rate with respect to sulfur dioxide, we can determine its molar mass. So before proceeding any further, let's determine the molar mass. Or actually, the information provided before the diffusion rates was its mass percent boron. So let's look at its mass percent boron first and determine its empirical formula. If we have 100 grams at 78.14% boron, would have 78.14 grams boron. We divide by the molar mass in order to get the moles of boron. What's left out of 100 is 21.86% hydrogen. So a 100 gram sample would have 21.86 grams hydrogen, which we'll convert to hydrogen by dividing by the molar mass hydrogen. So for every 7.228 moles boron, we have 21.687 moles hydrogen. We divide by the smallest in an attempt to get whole numbers, and we get 1 and 3. So the empirical formula would be BH3. Okay, now let's use the rates of effusion to calculate the molar mass of this compound. We take the ratio of the rates of effusion. Each rate is defined as the volume that effuses per unit time. This is the rate for the effusion of sulfur dioxide. This is the rate for effusion of our unknown boron hydride. That will be equal to the square root of the molar mass of our unknown boron hydride divided by the molar mass of SO2. A little bit of algebra then allows us to rearrange this equation to solve for the molar mass of our boron hydride. And we get 27.68 grams per mole. The empirical formula gives us a molar mass of 13.83 grams per mole. So to determine the molecular formula, we need to divide the molar mass of the empirical formula into the molar mass of the molecular formula, the one determined from Graham's law of effusion, and this gives us 2. So this will then be our subscript multiplier that we multiply the subscripts by in the empirical formula to get the molecular formula. So the molecular formula of this 4th boron hydride that was a gas is B2H6.